we'll start. Everyone's quiet. It's a good time to do that. Our next group presenting is Cache Creek. They'll have 25 minutes to present, and then we'll have 15 minutes for questions. We ask you to put their questions to Tilly.
Hi everyone, and welcome to our group project defense, strategies to control mercury pollution in the Cache Creek Basin, Northern California. My name is Bethany, and I'm one of the group members who worked on this project. I'd also like to introduce our other group members, Melissa, Nick, Krista, Amy Beth, and Toshi. Our presentation today will consist of a brief introduction to the Cache Creek Basin, its mining history and mercury implications, our project approach, which includes our decision trees, decision matrices, a watershed model, and several case studies. For this presentation, we are only going to include one case study to further illustrate our approach. We'll also talk about our project applications and our project summary. So where and what is the Cache Creek Basin? The Cache Creek Basin is located in Northern California and occupies almost 3,000 square kilometers. The northern part of the basin is within the California Coast Ranges and consists of low mountains containing forests, shrubland, grazing land, and some farmland. The southern part is within the Sacramento Valley and consists mostly of farmland. In addition to these land uses, the Cache Creek Basin has other beneficial uses. In particular, the water from Cache Creek is used for drinking water, irrigation, wildlife habitat, and recreational activities like fishing and kayaking. Unfortunately, the Cache Creek Basin has a high mercury pollution throughout the basin. This mercury pollution comes from natural sources like geothermal springs, but also from abandoned mine lands spread throughout the basin. Mercury mining in the basin began in the mid-19th century to assist in gold extraction from ore during the booming gold mining industry. The last mine closed in 1971, just around the time when environmental regulations began. However, before this time, little was understood about the toxicity of mercury. When the facilities closed, waste rock and tailings containing high concentration of mercury were left on steep slopes that are highly erodible. In addition, most of these mines are near tributaries of the Cache Creek. When there is rainfall, the resulting erosion causes these tailings to end up as sediment in creek beds. Some of this sediment is even transported to the Sacramento River and even down to the San Francisco Bay Delta. There are three major mining areas within the Cache Creek Basin. The first area I'm going to talk about is the Sulphur Big Mine, which is on the left. It was one of the biggest mercury producers in California, and it contributed significant amounts of pollution to Clear Lake. In 1990, the EPA designated this area as a Superfund site. And in 2002, the Central Valley Water Quality Control Board set a total maximum daily load, or TMDL, for mercury. A TMDL is set up to help local water bodies to meet water quality standards as required under the Clean Water Act. The other two areas are districts that contain more than one mine. The Knoxville district on the bottom contains 3 mines and is within the Davis Creek watershed. The other area is the Sulphur Creek mining district in the top right, which is within the Sulphur Creek, Sulphur Creek, Bear Creek, and Harley Gulch watersheds. The Sulphur Creek mining district is the largest district within the Cache Creek Basin and contains 12 mines. If you look on the map, you can see that the Sulphur Creek drains into Bear Creek, which means the mines within Sulphur Creek actually impacts the water quality for both and eventually the Cache Creek further south. The red lines you see on the map are impaired streams, so they have a TMDL requirement for mercury. Landowners who own land with one of these streams must attain the level of mercury allowed to help prevent adverse mercury effects on humans and wildlife. But what are these adverse effects with mercury and why are we so concerned about it? Before we begin, we must mention that there are different forms of mercury, and methylmercury is the one we are most concerned about. It is the most toxic, it can accumulate, and it's the most bioavailable. However, all mercury is a potent neurotoxin that affects the central nervous system, especially during the developmental phases of growth. In addition, mercury can also biomagnify, which is when the concentration of mercury increases as it moves up the food web. For example, an invertebrate may contain a small amount of mercury that is not harmful to humans, but as that mercury travels up the food web to a piscivorous fish like a striped bass, it may contain mercury levels that are harmful to humans. In addition, mercury can also bioaccumulate, which means an organism absorbs mercury in its tissue faster than it is lost. For example, the northern river otter may eat one fish that is contaminated with mercury, and that mercury is stored in its tissue. When it eats another fish that's contaminated with mercury, that mercury is also stored within its tissue. and then mercury over time essentially accumulates because it cannot be lost quick enough. There's also downstream impacts that people are concerned about within the Cache Creek Basin. At least 30% of the mercury found within the San Francisco Bay Delta is from the Cache Creek Basin. This has people concerned about the impact the basin is having on areas downstream, especially within the Bay Delta, and the effects it has on wildlife and its fish. Therefore, landowners must find strategies to restore and to remediate the basin to help protect wildlife and humans within the basin and also downstream. One such landowner is our client, the Bureau of Land Management, or BLM. The BLM manages approximately 26% of the basin. And if you look on the map, the area in green highlights their land ownership. They also manage the 110 square kilometer Cache Creek Wilderness. The wilderness was designated in 2006 by George W. Bush. As an owner, they are responsible for maintaining water quality and preventing ongoing discharge of pollutants. This means they are required to meet the TMDLs and any cleanup orders they receive. A TMDL is for water quality standards, but a cleanup order is given when an area is suspected to contribute to water quality degradation. In the case of the Cache Creek Basin, most of these cleanup orders are given for mines. The BLM currently has 3 cleanup orders for mines on their land. Because of the enormity and complexity of mercury and its ecological effects within the basin and downstream, mercury remediation is an important and difficult problem to solve. We were asked by the BLM to help with mercury remediation and restoration for their land. We want to achieve this by identifying different remediation and restoration options to help restore the basin. We wanted to develop a method to determine the best options for different sites. We want to evaluate management options through watershed modeling, and we wanted to assess the legal constraints with these different options. We accomplished our objectives in 3 different ways. We first created 3 different decision trees to help with site selection, management options, and which options are most efficient. We created decision matrices to help quantify and qualify a location and its options. And lastly, we used WARMTH, which is a watershed modeling program to look at mercury transportation in the basin and how different remediation and restoration options affect mercury transport. I'm first going to talk about our decision trees. This is our first decision tree, which asks general questions about the site, such as, is BLM the landowner? Is the site easily accessible? We used it to identify whether or not a site is a good candidate for restoration. If you look at the first one of the questions, which is the site located in the wilderness area, a no answer has you move on to the next question. A yes answer has you determine an alternative site, and this is because of the legal constraints with the wilderness area. When you reach the end of the tree has you determine appropriate remediation or restoration techniques, which is our second tree. So our second tree outlines different restoration and remediation options that are most appropriate for the Cache Creek Basin. We know this is really hard to read, so we're actually going to look at this one area to further describe this tree. So this tree asks a series of questions about each option. A yes has you go to the next question for the option, and a no disqualifies the option for further consideration, except where indicated, like with the Southern Basin construction option. We're actually going to look at this one as a further example of how to use this tree. If you look at the first question is the mercury present in suspended sediment? If the answer is no, then this option is disqualified for further consideration. If the answer is yes, you would move on to the next option, the next question, which is the site an existing settling basin? We would continue on down the tree using the same yes and no criteria. When you reach if all the answers for the option are answered yes, then you would retain this option for our next and last tree. This is our last decision tree, which takes all the options from the previous tree and determines which options are most effective and efficient when options are most effective and efficient. It asks questions like, does it effectively reduce mercury? And does the result likely meet the TMDL? The high, medium, and low you see are used to rank the options to determine the best one at the very end. These three decision trees are starting points to gather basic information to prioritize sites. They are also generalized to facilitate a wider use to areas outside the Cache Creek Basin with legacy mercury. And now Melissa is going to take you through one of our case studies the Harley Gulch wetland to further illustrate our decision matrices and watershed model.
Okay, so in our project report, we will be discussing 6 different case studies, and we chose different sites that had varying characteristics to test our approach under different scenarios. Today, we're going to be focusing just on the wetland, which can be seen here outlined in red. The wetlands are downstream from 2 mines, the Turkey Run mine that you can see at the top of the photo, and also the Abbott mine. Mercury comes down from these mining areas on small stream networks and goes into the wetlands where it becomes methylated and then goes further down into Harley Gulch, which can be seen at the bottom of our photo. Another thing to notice in this photo is that the wetlands are very close to a highway, which makes it easier to implement different remediation actions since the site is more accessible. This is a picture of what it looks like at the wetlands. You can see it's a highly vegetated area. It's also very flat. And again, you can notice the road in the background, so you can see how close it is. So now I'm going to summarize the results from our decision trees. This is the first part of our summary, the site characterization matrix. As we can see, the Harley Gulch wetlands is not a part of BLM land, but it is an important site to be remediated and restored in order to help BLM meet water quality objectives downstream. It's also not in a wilderness area, which makes it easier to implement different actions because there aren't as many policy constraints. Mercury concentrations in the area are between 5 and 20 parts per million, leading to a total amount of mercury between 135 and 540 kilograms. After we determined the characteristics of the site, we went through our decision tree to determine the best remediation actions. So this is summarized in our next matrix, the remediation options matrix. We chose the 6 most applicable strategies to discuss here today. The first is to do nothing, and this is just used as a baseline to judge other strategies against. However, you do want to note that there would be some monitoring costs associated with this. Our next strategy would be to remove sediments from the wetland, add fill, and revegetate the area. This would take a short amount of time, but it would be very costly, and removing the sediment would be quite invasive and lead to habitat alterations. Our next option, phytoremediation, is less invasive, but it would take a lot longer, anywhere between 5 and 20 years. There's also a chance that the root depths would not reach the depth of contamination in the area. Our next options start with a containment cap of clay. This again would take a short amount of time, but would be very expensive, and the contamination would still be there, and just be covered up so it wouldn't go into the ecosystem. And in the event of a large storm, they may be washed away, reintroducing the mercury into the area. Our next option is to construct a settling basin and catch the sediments before they move further downstream into Harley Gulch. This again would be fairly costly, however it would be pretty effective. In the event of high flows, the efficiency of this remediation option may be lower. Also, there's periodic maintenance required to take sediments out of the area when the settling basin begins to fill up. Our last option is to redirect flows away from the area and prevent methylmercury from going further down into Harley Gulch. Again, this would be fairly effective, however, there would be a lot of habitat alterations that occur. After determining the best options, we rank them based on their cost, effectiveness, and their time frame to work. We adjusted our rankings based on different types of decision makers that may put varying levels of importance on these parameters. Our first decision maker may have a low budget and therefore puts more emphasis on the low-cost method. In this case, phytoremediation would be the best option since it received the lowest score. Our next decision maker puts more emphasis on health effects and may want a remediation option that would be more efficient and effective. In this case, removal of sediments and a containment cap of clay are both considered the best options since they received the lowest score. However, removal of sediments may be better since a containment cap of clay has a risk of being washed away. So, again, after ranking our options, we decided that phytoremediation or excavation are the best when evaluated on their cost, effectiveness, and time frame. No, none of these options are likely to meet the TMDL. However, they would help to meet water quality objectives downstream. Upstream remediation may be necessary to further meet the goals of the TMDLs. And we can look at the effectiveness of our options more closely by using our watershed model for further analysis. This is an example of our watershed model, WARMP. WARMP is a modeling program that's used to track changes in water quality parameters through time, and you can explore the effects of reducing point and non-point sources of contaminants. It has been used to evaluate other TMDLs, and it is one of the few watershed models that deals with mercury. Here we can see the outlines of the subbasins for Cache Creek, as well as the stream networks. There are two major reservoirs in the area, Clear Lake and the Indian Valley Reservoir. However, we focused our modeling efforts on the mining areas. Mines were modeled as point sources, and by varying the levels of these point sources, we could simulate different remediation actions. WARMP also takes into account mercury chemistry and the methylation-demethylation processes, allowing us to further see if we can meet the TMDL with different remediation actions. This is an example of some output from WARMP showing the hydrology. The blue line represents modeled hydrology, and the black dots represent observed data points. So as you can see, they follow each other pretty closely, showing that our model has been calibrated well. After we've calibrated the model, we could determine the relative levels of total mercury and methyl mercury in different areas of the basin. In this example, the gray line represents total mercury loads. The thickness of the line is proportional to the magnitude of the load. Using the WARMP model, we simulated reducing all mines in the basin. Upstream at Harley Gulch, we saw a decrease of 13 kilograms per year to 6.5 kilograms per year. At Sulphur Creek, we saw a decrease in loads from 24 kilograms per year to 12.5 kilograms per year. Unfortunately, this would not meet the TMDL, which calls for a 95% reduction of loads. Further downstream at Rumsey on Cache Creek and at Yolo on Cache Creek, we see even less of a decrease in the loads. Each one only decreased by about 6%. This shows that there is a need to find the areas with high background levels of mercury and then to implement erosion reduction measures. These results also reflect the fact that mercury-enriched sediments from the mining areas are slowly moving downstream, along with mercury from natural and unknown sources. Now let's talk about the potential to lower methyl mercury concentrations in Harley Gulch by remediating the wetlands from our case study. In WARMP, we simulated the effects of a remediation action by lowering the amount of mercury in the wetlands. The remediation action did not have an immediate impact, so we simulated the effect of this remediation over time by decreasing mercury levels downstream in Harley Gulch, which is expected to occur a few years after a cleanup. We decreased the mercury content in Harley Gulch by half, and the results of this are shown in our graph. The graph shows a reduction in methyl mercury over a 2-year period from our model. The blue line shows methyl mercury concentrations in Harley Gulch before a cleanup, and the red line represents what would happen after one. So you can see the levels were reduced pretty greatly. However, they do not meet the level of the TMDL, which is the green line at the bottom of the graph. So now I'm going to talk about some of the applications and future research that may be necessary to further look at the questions from our project. So we brought up the question about whether or not the TMDL is feasible in the short term for BLM. However, we have tried to provide BLM with strategies to make progress even if they can't fully meet the TMDL at this time. We've also made a framework in order for them to assess other areas besides the Cache Creek Basin. Another question that was brought up during our research was trying to fit the need to plan low footprint, low cost technologies, given that many of these are still in development and have not been tested extensively in the field. This brings up the possibility to use Cache Creek Basin as a testing ground for these emerging technologies in the future. So in summary, we've identified the sources and relative contributions of mercury in the basin using our watershed model. We've done a comprehensive evaluation of mercury remediation and restoration options, looking at their cost, effectiveness, and time frame. We've made decision trees to not only look at remediation actions, but also assess policy issues that may affect their implementation. And then we've implemented WARF, or watershed model, to evaluate these management options and see how they may help to meet water quality objectives downstream. These are the people we would like to thank. And now we'll open up the floor for questions, first from our panel and then others.
Very nice presentation, really amazing project. You mentioned at the very beginning natural sources, and I'm wondering if you could clarify more about that. So is this differentiation potentially between sources from mining versus natural sources? Are those differentiated in the remediation, evaluation of remediation strategies, or is that not possible? And what is the magnitude of the natural versus mining-related sources?
So natural sources can include mercury-enriched soils, and as well as saline groundwater that has high concentrations of mercury. We didn't really differentiate those in our remediation options, as it's all mixed together and it's hard to pull those out.
Well, there's several ways to try to reduce the natural background areas. First, you have to identify them, and that really hasn't been done yet. And then this is kind of where the BLM comes in. I mean, a lot of the area is wilderness, and so grazing and roads aren't allowed, and so there's not maybe a whole lot you can do in that area, but areas that do have roads, grazing, firewood collection, logging, any sort of human activity, you know, those areas, there could definitely be sort of management practices done to reduce the erosion that happens in those areas.
Oh, sorry, just as well as they have a lot of off-highway vehicle recreation in the area, and that leads to a lot of erosion.
Okay, very good, thanks. Other contaminants, so mining actually brings forth a lot of other, mercury is certainly very serious, but are there other metals that are of concern, and might your approaches also be sort of incidentally addressing some other contaminant concerns that aren't the focus of the TMDL? Is that an added benefit of this project or this approach?
Well, it wasn't really the focus of our research, and in looking through a lot of the research in the area, most of the focus has been on mercury and not the other contaminants. It doesn't seem to be as high of a priority.
So there's not much data on the other
Not that
metals?
we've found, no.
And then I guess my last question for now is, if the TMDLs are not really achievable, I'm really perplexed by, I mean, my understanding is that when TMDLs are set, there's some modeling is performed to evaluate the feasibility of achieving and looking at implementation. But if they're not achievable, what's sort of the regulatory and maybe political horizon for this basin, and how does your study sort of shape what might potentially change about, the further, I guess, expectation that these TMDLs will be achieved?
Well, the focus of the TMDLs have been on a level that's acceptable and not necessarily, it's somewhat achievable in the long term, I guess, is part of the issue, is if you cut off all of the sources of mercury and then are able to deal with the mercury levels that are in the stream beds and the erosion and deal with every source of it, then it could be achievable, but it's difficult to actually get to that point because there is still a lot of data that is that they're unsure of. There's especially one stretch of the Cache Creek where they know that there's an increase in mercury in that area, but we're not exactly sure what the sources are. So to remediate them is a bit difficult, and that's most of the difficulty of meeting the TMDL, is not knowing exactly where you should focus your attention.
So you're optimistic based on the fact that the levels can come down according to the strategies that you study, but yet, even though you're not showing that the projection is that they would come down low enough within this case study.
Well, yeah, most of what we looked at was cutting off the sources of the different mines, and would that meet the TMDLs, and just doing that alone wouldn't, and that's most of our focus. I don't think that.
Yeah, I mean, the reason why it didn't meet the TMDL in the Harley Gulch is because the natural levels are so high that it doesn't ever get
Okay.
down there, but it's the responsibility of the responsible parties to reach the background levels and sort of the naturally occurring levels, and then I think it's up to the regulatory body to decide what to do after then, but first they have to reach the background levels and do all they can before that point's reached, and there needs to be a lot of monitoring that goes on, because right now, after remediation, I don't think people really know what the mercury concentrations are going to be and how fast they're going to decrease.
Thanks.
Well, let me start by saying I'm really impressed. It's a good presentation, but it's also a good grappling with a tough subject. You struggle with deal with a problem that has this many moving parts and so forth. So what I saw a while back was a focus on one area you've shifted. I think this is a huge improvement. It's very, very valuable. I like the methodology. A few suggestions. You might want to talk just briefly about how we got into this mess. So why did they do all this mercury mining in that area? You know, what was the genesis of that history? And then maybe more to this TMDL question with the Clean Water Act. What exactly is that? And what's the problem? But I really like the way you created a method to focus in on doing something about some part of the problem and coming up with, you may not solve everything right away, but at least you've got a reasonable and logical way to get going on. So I think you made a contribution to the issue of the BLM to have some, reasonable approach to move forward. I don't know if I have a lot of questions. We've been through a lot of discussions on homes already, so I'm impressed. I guess maybe the big question is, what's your kind of stepping back from this? What's your long-term prognosis here? If one were to spend 50 years picking off these accessible sites with kind of using your method, what's your sense? And the problem's been around for 150, right? They started digging all that up in the mid-1800s, so we've had it for 150 years. It may take some time to fix, but what's your sense?
It's a difficult question. I think there's a lot of room for improvement. I definitely think there is, but as Nick has pointed out, there is some natural elevated levels in the soils, so I don't know if it'll ever be an ideal situation. So I don't know if you have anything to add.
I mean, when I simulated the cleanup of all the mines, and it only reduced mercury at YOLO by 6%, and I don't know if that's necessarily right, but all the data that I calibrated the model with, that's the answer I get. So whether that extra mercury is background, there's not a whole lot you can do about it, or whether it's in the stream sediments and it's moving down slowly, kind of depends on what's going to happen in the future. So I think there needs to be a huge effort to find where that mercury is coming from, and a lot more samples taken from a lot more different areas. And the thing that 300 kilograms a year of mercury moving down the canyon was a yearly average, but in a year like 1998, there's 1,000 kilograms, and then in a year like 2001, there might be 50 kilograms. So, most of the mercury comes down in just a few days in the really big storms, and so just those samples haven't been taken, so it's almost impossible to get there, and then it's almost impossible to sample at the right times to even identify what these sources are. But I think there needs to be more effort done to do that.
Can I ask another question about fire remediation? Does it permanently remove mercury? Like, does it facilitate volatilization of mercury into the atmosphere? What's the process? Maybe it's beyond the scope of your project, but in case you ran across that.
Yeah, there's a couple of different, some plants do volatilize it and it goes up into the atmosphere, and then others just store it and reduce the emissions.
And then those plants would have to be harvested somehow and managed?
Yeah, most likely.
Partial elevation is several types of partial elevation, and one is partial extraction. So then, Mercury before volatile Mercury, it is extracted, and one consideration is possibility of air pollution. Then it's one of the considerations.
We had a backwards one.
You have the plans open, so.
Yeah.
Right.
Oh, yeah, we have an example of some plans.
Did you run across studies by the USGS in the Everglades about mercury and trying to remediate it using natural? Just curious if you ran across. There's been quite a bit of work in Florida by USGS. Conversion of
We haven't looked into that.
methylation and demethylation.
That was something we can look into for.
Yeah, Ron,
I have seen a few papers, didn't really get too in depth into them, but
yeah, they look at methylation and demethylation in sediments and for Everglades. Ron Orman's been a leader in that work. Very good stuff.
Good. Do you have any questions for our client from BLM?
Well, thank you. I think you guys have done a tremendous job. The work that you've done is far greater than what we would do in our own agency. So it's already phenomenal. So I really appreciate that. It would be good to have a chance to talk with you, maybe to help clarify some of the points of questions that people ask and any other questions that you might have. There is only a little bit of information about the other potentially toxic or contaminant elements, and also asbestos is a concern in the region as well. But I'm amazed and concerned that you were only able to detect a 6% change in the KK Valley in Rumsey. And I'm wondering how did you model the actual 150 years of sediment that might still be in the creek beds? Because one of the issues that we have is indeed, we can remediate at the mine site, but then the Central Valley Regional Water Quality Control Board has also been looking at sediment accumulations in both Cache Creek and Bear Creek. We don't have any data for Harley Gulch yet, but I was wondering if you were able to include that in your modeling, and maybe that would explain why you're getting such a small decrease.
Yeah, well, it doesn't really handle bed scour very well. I mean, you give it bed sediment, you give it a mercury concentration, but it doesn't. But you can't say it's scouring a certain amount every year. As far as I've found, at least I haven't found how to do that. You can give it a bank stability factor, and that helps erode, but you can't say, okay, now the banks are 2 parts per million mercury. So as far as that was modeled, yeah, I mean, we couldn't really take care of that too well, but they did do the Cache Creek Canyon mercury inventory paper that came out 2 years ago, and there was also a following Bear Creek mercury inventory paper, and the Cache Creek Canyon they found only has 2,200 kilograms of mercury, and the Bear Creek Canyon only has 92 kilograms of mercury. So the amount of mercury that they're finding passing by Rumsey, I don't think it could be found in the canyon. So I feel like their estimation of the amount of unknown mercury that's coming from bed sediments is, I think it's been overestimated. I think maybe it must be coming from other sources more than bed sediments. But I haven't been able to model that.
Did you try to include any atmospheric deposition or evaporation in your model at all? Or was that?
Atmospheric deposition, it hasn't, there's been several reports that said it's not that big of a deal.
Yeah.
It's really insignificant.
questions?
Cool.